In this video we're going to look at how unitary matrices allow us to elegantly change bases. Now, what do we mean by that? Well, normally we think of x as a vector chi0 through chi m minus 1. And what that really captures is that you're taking chi0 times the first standard basis vector plus chi1 times the second standard basis vector, and so forth. In other words, you're taking a linear combination of the standard basis vectors, which form a basis for Cm. And this is another way of writing the same thing. Now, it may be more convenient or better for some reason to view this vector with respect to a different orthonormal basis. Okay, say u0 through um minus 1. Now, notice that if u0 through um minus 1 form an orthonormal basis for Cm, then you should be able to write x as some constant times u0 plus another constant times u1 and so forth, which of course we know we can write as the matrix u times a vector that are the coefficients for vector x, but now viewed in this new basis. Okay, now, how can we elegantly go from one to the other? Well, here we go. X we can write as the identity times x. Okay? But because U is a unitary matrix, we know that that's the same as U times U Hermitian transpose times the vector x. Okay, oh, well, we're starting to get close because this U here is what we have right here. And U Hermitian transpose times x is a vector, which then should give us the coefficients that we desire. Okay, now we can go into a little bit more detail and say, well, that's just equal to U times the matrix U written as its columns but transpose. So that gives us U0 Hermitian transpose as the first row, U1 Hermitian transpose as the second row, and so forth. Um minus 1 Hermitian transpose times the vector x. And that we know because we know how to multiply partitioned matrices times a vector. That's just equal to U times the vector U0 Hermitian x, U1 Hermitian x, and so forth. Okay? And that tells us that you can either take U and multiply its Hermitian transpose times x to get these coefficients that allow you to view in terms of this new basis, or you can form that vector more explicitly as follows. But regardless, alpha sub j is just equal to U sub j Hermitian transpose times x. And bingo, we can take a vector and we can view it in terms of a new orthonormal basis.